Okay, so this is Physics 1C for Tuesday, May 5th. Today we're going to continue talking about AC circuits. Let's get things set up. Full screen on this. This one. Alright, so last time, just to summarize what we did, we introduced the concept of Phasor diagrams, and we used them to describe what happens when you put an inductor, a capacitor, and a resistor individually into a circuit. And just to kind of summarize what we did last time, we said that when you have a circuit that only has an inductor, there is a kind of mnemonic device that you can use to memorize what happens, which is ELI. And inside of a circuit that only has an inductor, we said that you're going to get an equation for the electric potential or the voltage across the inductor as a function of time. That's going to look something like this. It's going to be V max times the cosine of omega t. And this is where these are all going to differ. All of these are going to start the same way. You're going to have VL of t is V max cosine of omega t something. Now, in this case, the EMF needs to be ahead of the current. This is how this works. It's EMF leads the current. And it's going to lead the current by a factor of pi over 2. So here we're going to write plus pi over 2. And then I'm just going to check to make sure that's right, because I don't want to get started off on the wrong foot here by looking at our notes from last time. And make sure that when we had the inductor, which is this right here, yeah, that's what we got. Omega t plus pi over 2 for the inductor. Now, another piece of this that we learned about last time was what the value of V max is in this case. So I'm going to put that over here as well, because this is obviously going to be important for what we're doing today. In the case of when you have just an inductor, the maximum inductance, or sorry, the maximum voltage across the inductor, which I could just call VL, or we can call it V max, I guess, is going to be equal to I times omega L. Yeah, I think calling that VL is better. Let's do that. So this is VL. We'll just call that VL. Or we can write this as I times the quantity X sub L, where X sub L is what we call inductive reactance, and it's equal to the frequency multiplied by L. So that's the inductor-only circuit. We also did the capacitor-only circuit, for which the mnemonic device is ICE, so the current is going to lead the EMF. For this one, we're going to have the voltage as a function of time across the capacitor is going to be equal to Vc times the cosine of omega t. So it starts off the same, but then now we're going to have minus pi over 2, because in the capacitor-only circuit, the current leads the EMF by, the current leads the EMF, so that this makes us write down the current equation. The current equation is this. So this is kind of our baseline. The current as a function of time is I max cos omega t, so if you want the current to lead the EMF, you need to put a minus pi over 2 here, because then the current is ahead by pi over 2, right? Whereas in this case, in the inductor-only case, the voltage is plus pi over 2, so it's ahead. So that's what we learned last time. We also learned what Vc was. So the maximum voltage across our capacitor can always be given by the current flowing through the circuit, multiplied by, or actually it's divided by omega c, where the other way we write this is I times Xc, where Xc is what we call capacitive reactance, and it is equal to 1 over omega times c. XL and Xc both have units of ohms, and yeah, so these are all the things that we learned about last time. These equations and these new quantities that we developed. So what we'd like to do today, I guess first of all, is just to ask, were there any questions from last time about what all the stuff I just wrote on the board here? Does anyone have any questions about all these equations and these relationships for AC circuits? It's been quite a few days, right? It's probably been 5 days since we met last, so I would understand if you all have questions.
The values X sub L and X sub C that you wrote, those are supposed to represent how the inductor and the capacitor react to changes in current, right?
Yeah, exactly. Exactly. It's a way of basically taking your inductor and your capacitor and effectively turning them into a resistor. If you think about it like that. It's basically, you're kind of like, you're coming up with like a, what's the word for it? It's like a common, some kind of common ground upon which you're going to talk about resistors, inductors, and capacitors. We know that inductors respond to high frequency current because that's what an inductor does. It doesn't like changes in current, right? So that means that if we're going to write an inductance times a frequency, that's going to give us effectively a number that represents how much the inductor resists, not really just changes in current, but also just resists current in a way. Because now that you have the quantity, it acts basically just like a resistor. Again, compare both of these two equations to our the equation that we're kind of relating them to, which is V is equal to I times R. But yeah. Because like once you've gotten rid of the omega, and you just have XL or XC, they act just like the resistor does, right? And all I mean by that is by saying that they obey the idea that if you take the voltage and you divide by the resistance, that gives you the current, right? This is a very simple relationship because you can just look at it and say, suppose that I give you a voltage of 110 volts, and that's fixed. Then what can you do to increase current? Well, the only thing you can do is make resistance smaller, right? That's all you can do. And you can use the same logic on VL equal to IX and VC equal to IX as well, because they have the exact same mathematical relationship going on. So at the end of the day, what this is going to do is it's going to make analyzing AC circuits a lot simpler than, for example, analyzing the circuit that Cam was asking about at the beginning of class before we started. Okay, so what we do now... Oh god, I didn't mean to do that. I don't know what I just did. I'll fix that later. The next thing we're going to do is to basically put all three of these things together. So we're going to look at a Series Rlc circuit. This is what the majority of your homework problems in this chapter are going to be based on, is by looking at the Series RLC circuit. So what does this look like? Well, all we need to do is to have a voltage source. Remember that your voltage source is going to look something like this. And then we're going to connect up to this a resistor, leave some space, a capacitor, and an inductor. It does not matter what order we put these in because the current doesn't really care what order they're in. All that's going to matter in terms of what we're doing right now is that they're in series as opposed to being in parallel. Okay. So the next thing that we're going to do is, on our picture right here, I'm going to put little voltmeters. So this is going to be V sub R. That's going to vary as a function of time. We're going to have another voltmeter for here. This will be VC, and this will be VL. So we're basically just putting infinite impedance voltmeters or infinite resistance voltmeters that will not... These are not going to change our circuit in any way. The idea is they have a huge amount of resistance, which means that any current flowing in our circuit... So let's put our current on here. Our current's, let's say, going to flow this way at a moment in time. Remember, the current is going to be also a function of time. So everything in this circuit is going to be a function of time because the voltage is also alternating back and forth. In addition to all of this, we're also going to put one other voltmeter across here. So I'm just going to say V sub S is going to so S stands for source. And the rest of them you can figure out. So this is our AC voltage source, and we'd like to be able to know effectively what VR, VC, VL, and VS are in this case. Keeping in mind that we're going to use our baseline of the current as a function of time is going to be written as Imax cosine of omega t. That's going to be our baseline. We're going to use this, and our goal is to calculate what the voltage of the source as a function of time is, VR, VC, and VL are. Yeah, that's what we're trying to do. So using what we had from before, so let's copy paste these down. This one, and then I'm also going to write down what we got for the resistor, which is basically somewhere in between these, which is that the voltage across the resistor is a function of time. This one is just given as VR cosine of omega t, because the resistor is always going to be in phase with the current. If the current's flowing right. Okay. So now in order to analyze this circuit, we're going to use the kind of technology that we used last time, which is our phasor diagrams. So we'll start off with coordinate axes. And now what we're going to do is we're going to draw our phasors in. So we'll start off with a phasor to represent the current. We'll use purple for that. And let's say the easiest way to do this, I feel like, is to put everything on. I'm gonna do it like this. We're gonna have. Yeah, I feel like that's kind of lazy. So here's our current. This is our current phasor. Remember that the current phasor is set up so that the length of the phasor is I max. And the angle made right here, what is that equal to? Does anyone remember? When I'm drawing these phasor diagrams, what's the angle made with the axis always defined as?
Omega t.
Omega times t, yeah. Because the idea is, when t is equal to 0, this phasor lies on the axis right here, and the current is equal to I max. And then omega times t says, suppose omega is something simple like 2 pi radians per second. If omega is 2 pi radians per second, how long is it going to take for my phasor to go from its initial position here at t equal to 0 all the way around 1 time? Supposing that omega is 2 pi radians per second. How long will it take? For this?
Just 1 second.
1 second.
1 second. So what you should imagine in your mind is that you have this little arrow that rotates around once every second. Every second it goes around 1 time, basically like this. And if you do that, then the projection of this phasor onto the x-axis will always tell you what the current at a moment in time is, right? So for example, after half a second, when the phasor is pointing this way, the current in the circuit is going to be negative I max, right? And so on and so forth, right? When we let a quarter of a second pass, then the phasor is going to be pointing straight up, and at that point, what will the current be?
0.
It's 0 because the projection of a phasor that points straight up onto the x-axis is 0, right? All right. And of course, if you just plug in the numbers, that's still going to work out, right? Because if I tell you omega is 2 pi and I plug in t is equal to a quarter, right? Then you're going to have 2 pi over 4. And you're going to be taking the cosine of that. Well, that is, you know, and I'm pretty sure the cosine of pi over 2 is 0, right? So it works out whether you use the math or the phasor, it doesn't really matter. But this is where the phasors become really useful, is we can ask the following question. What is Vs going to be equal to? You know? What is Vs going to be equal to? Or a better question to ask is, we know when we write down the voltage as a function of time across the inductor that we get this, I guess this got erased, we get this term VL, right? And we can calculate the maximum voltage across the inductor because we know that VL is equal to I times XL. So if I give you a value of current and an inductance and an omega, you can calculate VL, right? But what would Vs end up being? What is this equal to?
It's something like V total times cosine of omega t plus something.
That's right. It's going to be something like a cosine function, and it's going to have an omega t in it, and it's going to have some... So, but my question specifically here is, so what you answered, and I'll write that down. What you're talking about is this. V sub s of t is going to be equal to some... We're just going to use the same notation that I'm using here. We guess that our answer is going to be something like cosine omega t plus something, right? And, I mean, just to tell you in advance, there's going to be a phase angle right here, and we're going to calculate what this is, okay? This is what we're going to calculate, okay? But my question is, before we even do that, what do we predict the answer for this quantity is here? Kind of think about this as like the total voltage in the system, right? What do we think this is going to be equal to? is it going to be equal to something like VL plus VC plus VR? Or is it going to be equal to something else?
Yeah, I was thinking maybe like a sum.
Something like a sum.
Since they're all in series with each other, right?
Yeah. Now, DeHao's right. It's going to involve adding vectors. It's not going to involve just adding them directly. Because these quantities are not going to reach maximum at the same time. You know what I mean? These three will not have... And I don't think you can find a time, it's not possible, you can try if you want to, when VL is equal to capital VL. Basically, is there a time when every one of these quantities is equal to 1? You know what I'm saying? And I think the answer is that's impossible, right? If all of these quantities were equal to 1, then this would be true, right? If there was ever a time when all three of these quantities were equal to 1, then you could just say, well, then the maximum voltage in your system, the voltage of the source, would just be the total maximum voltage of this plus the maximum voltages plus maximum. But the reality is they're not in phase with each other, right? They're all out of phase with each other. So that's not going to happen. This is not going to be what we get for our answer, although that might be what you predict. In addition, you could even go as far as to ask, what would the little vs? Remember that little vs represents the instantaneous voltage, right? So you could even ask the question, well, is this going to be equal to VL plus VC plus VR? I don't know. We'll have to address that later. We'll see if this is true or not. I mean, it looks like in the picture that they are, right? Like if I tell you that I know, if I can look at these voltmeters and I can look at this voltmeter, you know, and let's say that this one was 1 volt, this was 2 volts, and this was like negative 1.5 volts, then you would think that this one would read whatever the sum of these is, right? 3 minus 1.5, so it would be 1.5, right? You see what I'm saying?
Mm-hmm.
Yeah.
That's what you probably think, but let's see if that's true. I think
So
that the reality is that's not going to happen, but we'll see at the end. What's up?
So the maximum source is not the sum of the component maximum voltages.
The maximum of the source is not the sum of them. Yeah, exactly.
Okay.
That's right. It can't be because they're not in phase with each other, right?
Mm-hmm.
Okay, so in order to answer these questions, what we're going to do is we're going to draw phasors for each one of our vectors here. So let's start off with VR, because that's the easiest one to do. We know that VR of t and I of t are in phase with each other. They're both given by cos omega t. So that omega t tells you the angle between the x-axis and the vector. So there we go. That's VR. The length of this vector is going to be VR. Okay. It's going to be that. Alright, then we need to put in here our VL and VC, keeping in mind that VL needs to lead the current phasor by a total of pi over 2. Basically, this represents the angle between the x-axis and the phasor. So, if I put a phasor in here for VL, do I want to point it this way? Do I want to point it this way or something else? Is it going to go into quadrant 2 or quadrant 4 for VL?
Quadrant 2.
Yeah, quadrant 2. And the angle between these two right here needs to be a right angle, right?
Yep.
Now let's make this just a little bit longer for demonstration purposes. Okay. So the length of this vector, I'm just going to write is V sub L, and you can hopefully, I don't know if I need to put a right angle right here, but I'm not going to, just to keep things kind of clean. The undo is just not working today. It wasn't working last time either. What's going on? Undo, undo, undo. It's not doing anything. Control Z. There we go. So that's VL. We also want to throw in here VC. Maybe we use a slightly different color for VC. So for VC now, VC has omega t minus pi over 2 as its phase, right? So when we draw that on here, we need to draw it 180 degrees opposite to VL. Something like that. I'm going to intentionally make this shorter. This isn't always going to happen. It's just going to be nice for this problem right here. Okay. So there we go. Now, as DeHao said, what we're going to do now is we're going to notice that VL and VC happen to be exactly 180 degrees out of phase with each other, and they always will be. That's just how that's basically, if you look at these two equations right here, you can tell that if this one is ahead by pi over 2 and this one's behind by pi over 2, and you can really see it in this picture, that VL and VC will always be 180 degrees away from each other. So we know that since these phasors basically act very similar to vectors, what I can do is I can construct a new vector that is just going to be the sum of VL and VC, which in this case they're opposites, so we're going to subtract them, right? So what's that going to look like? Well, if I take this vector and I subtract off this vector by just like putting them on top of each other here. It's always really funny how like things look like that really looks like a straight line, but then you put them on top of each other and you realize that they're not. That's okay though. So if I put VC right on top of here, it's going to look something like that, right? So, I guess in another color, just to be clear, I'm going to put a new phasor that's going to be the sum of those two. I don't know why I drew it that way. It needs to go from the origin up to this point. So now, this phasor is going to have a length of VL minus VC. That makes sense to everybody? So the final thing to do is to draw a vector that is going to be, it's also a phasor, but it's going to be a sum of VR and VL minus VC. And that phasor is going to go from here up to about here-ish. And what I'll do is I'll use one of these as a measuring stick, just to get it right. So it needs to go basically out to there, right? There we go. So all I've done here is, hopefully if I remove this, you all still understand what I did, but I'll leave it here for just a second. I'm basically just vector adding VR and VL plus VC. Okay. So this is now going to be Vs. The length of this phasor will be V sub s. Alright. And the angle right here between
It's 90 minus omega t.
This angle we're gonna call
Actually, no,
That's like
phi.
5 or 4.
We're gonna call this angle phi. Okay. It's not related to omega t. It's real. I mean, no, it's not related to omega t at all. Yeah. This is just the angle between the source and the current. So it's actually going to be exactly what I did right here. Now, before we get into that and talk about what V-source is, let's start to put all these things together. Now, on my picture right here, I basically have a right triangle right there. And I can make the following statement. Vs should be equal to Vr squared plus this vector squared, right? So let's write that over here. So V sub s squared should be equal to Vr squared plus VL minus VC whole squared. Can you all see that from the picture?
Yep.
Okay, so this is pretty much the whole point of doing the phasor thing, is to get to this step, where we can now basically go through and vastly simplify the way we're going to understand this. So what we do is we're going to go back and we're going to plug in what we have for VR, VL, and VC. And I'll just scroll up just a little bit as I do this, because they're all written right here. So there's VC, and there's VL, right? And there's VR. So we're going to plug all of those into our equation now. So we're going to have Vs squared is equal to, so VR will become IR whole squared plus VL will become I times XL minus VC will become I times XC. Now I'll scroll back down. So the next thing we could do is we can notice that there's an I in every one of these terms. So we can factor that out. So we end up getting V sub s is equal to, I'm going to write it like this, I times the square root of R squared plus XL minus XC squared. Okay, so I kind of did 2 steps at once there. I factored out the I from every term, and it's I squared, but then when you square root both sides, it just becomes this expression right here. Everyone okay with that?
Mhm.
Yep.
The next thing to do is to define this quantity that's in the square root here as what we call impedance. So we're going to say let Z, capital Z, be equal to the square root of R squared plus XL minus XC squared. And we call this impedance. This is a kind of generalized type of resistance for a circuit that contains resistors, capacitors, and inductors, and it really only applies to AC circuits. I think that's true. I'm not an electrical engineer or electrician, so I may be wrong, but I think impedance generally is used to apply to AC circuits and not DC circuits. So when we let this be true, look at how simple our result becomes. So now the voltage of the source is just equal to I times Z. And that's it. The bigger the value of the impedance, the lower the current you're going to get. The larger the value of the impedance, the smaller the current you're going to get. It acts just like resistance, basically. You can almost think of it as being resistance if you want to. It has other properties that resistance doesn't have, but it's basically like resistance for an AC circuit. So does anyone have any questions about that?
Nope.
Okay. We can say a few other things about our picture right here. Now, the other thing we can say is now that we know what the voltage max of this is V max, right? Now we can officially say that, think about how we constructed these phasors. Our VR phasor was just, VR cosine omega t because it happened to line up with I max, right? And VL was cosine omega t plus pi over 2 because it was pi over 2, right, ahead of the current phasor right here. So there's a plus pi over 2. So if I have an object like the voltage of the source right here, which is ahead of I by phi, then we can also write down that the voltage of the source as a function of time is going to be equal to V sub s, which is now IZ, multiplied by the cosine of omega t plus what we call the phase angle phi. Okay, so phi is a phase angle. And it tells you just how much your voltage is out of sync with your current, basically. It tells you how much the voltage is out of sync with the current. If phi was equal to 0, then the voltage and the current would be in phase with one another. And what we're going to learn later on is that means that you're getting maximum power output, but for now it's just a phase angle. Now we'd like to be able to define what the phase angle is for calculations that we're going to do, and we'd also like to know be able to find out what the phase angle is because in some applications we're either going to want to reduce or increase this. So in order to find the phase angle, we can basically just use trigonometry. We can look at our picture right here and say phi is an angle in a triangle that has the following sides. I can write that the tangent of the angle phi, maybe you all can tell me, what would this be equal to? Remember that the triangle that I'm describing is this triangle here.
It would be VL minus VC over VR.
Yeah, exactly. Exactly. So the opposite side is VL minus VC, and the adjacent side is VR. So we just write VR. And then we make the same replacement that we did before. Does this make sense to everyone? Can everyone see where that's coming from?
Yes.
It's just a triangle at the end of the day. All of this works off of this idea. This is all you have to remember most of these. You can rederive all the things that I just did if you just remember this simple triangle. Angle is phi. This side is VL minus VC. This side is VR. And this side is VS. This is all you need to know to remember all of this stuff. It all comes from this triangle, in case you're ever getting lost or in case you ever want to use some other method to solve something, which may be useful to some of the homework problems you do. Well, what are these? Well, VL was IXL, and VC was IXC, and VR was IR, so the I's all cancel. So we end up getting that the tangent of the angle phi is equal to XL minus XC divided by R. And depending on which one of these quantities is larger, XL or XC, if XL is greater than XC, then phi is going to be positive, right? And if XL is less than XC, then phi is going to be negative. Does that make sense?
Mm-hmm.
Yep.
Okay. So these quantities, XL and XC, are really going to determine, they're going to determine the phase angle. They're also going to determine the impedance. What happens when XL and XC are equal to each other? You get phi equal to what?
The phase angle is 0.
0.
Yep.
Tangent is...
Yeah, the arctan of 0 is 0. So if XL is equal to XC, you get phi equal to 0. And you also get Z equal to what?
Just R.
Just R. Yeah. Okay. So that's going to be a special situation that we'll talk about a little bit later.
Is that when it becomes the projection of Imax?
Yeah. It'll be right on top. Yeah, VS will be right on top of I. Yep. Okay, what else can we say here? Well, there's another way that we can define phi, right? The other way we could define phi, there's two different ways. We can use a cosine or a sine, but the cosine is going to be useful. I would say a cosine of phi in this case is going to be VR over VS. But VR is IR, and VS is I times Z now, the impedance, this equation that we just derived. So that means that cosine of phi is R over Z. Again, this one's going to be kind of useful because cos phi itself is going to be something we're going to call the power factor. We're later on going to call this the power factor, and you'll see why. It is going to have an effect on the output power of our circuit. Okay, we got this, this, this. We've already defined these. We defined... Okay, I didn't write it down exactly, but... Oh no, I wrote it right here. There we go. Is that it? Did we do everything we need to do here? I think so. Because now what we can do is we can use these results to solve some problems. So let us do that. Our break timings are going to be really weird today because we started like pretty late, but that's okay. We're going to do these two problems. Okay. These LRC circuit problems are very, very, very easy. This is probably one of the easiest chapters in this book. Why is it doing this? Okay. This program is... It's either the program or... It's probably user error. It's probably my fault, but... A lot of really weird interactions with this program. Yeah, these problems, though, they're really straightforward. It's mostly just algebra. Almost entirely just algebra that you're using to solve these. Okay, so it says, in the series circuit of figure whatever, suppose we have this resistor, this inductor, this capacitor, this voltage, this angular frequency. We want to find the reactances, the impedance, the current amplitude, the phase angle. We're just going to calculate a bunch of stuff, basically, right? So what does the circuit look like? Well, it's the same circuit that we saw previously. In fact, we could probably just copy-paste it, because this picture is going to be what we need for this problem. So let's just copy-paste it. Come on, let me just... Okay, so there's our circuit, and we're given some values. Do I need to rewrite these down? I don't know. You can all read those, right? Is that big enough that you can all read it? I don't know. Maybe it's not. I'll write them over here. So we have R equals 300 ohm. L is 60 millihenry. C is 0.5 microfarad. V is 50 volts. I'm pretty sure this is going to be coming from the voltage of the source. So Vs is going to be what this is. It's like the maximum voltage across the source. This would be like something you would always know in a real experiment, because you'd always be using some source, some AC source, and it would have a number on it. Like it'd be like, this is a 50 volt source, or it'd be like a variable source where you could go from like 30 volts up to 50 volts, or 30 volts up to 100 volts, or something like that. This is always going to be something that you know, basically, is what I'm trying to say. All right, that's it. So we want to find, in order, we want to find XL, XC, impedance, current amplitude, which just means this means maximum current, phase angle phi, and the voltage amplitude across each circuit element. So, again, when it says voltage amplitude, when it says current amplitude, the reason it's saying that the reason it's using that language, amplitude, is it's kind of harkening back to your study of like sine curves and cosine curves, right? If I have a sine curve, then we define the amplitude to be the min and max of the curve, right? A is the amplitude, right? So when they say current amplitude, they mean maximum current, right? When they say voltage amplitude, they mean maximum voltage. And here, what was it? V equals 50 volts. This means maximum as well. All right. I don't know why they use that language. I feel like it's very confusing, but I'm sure they have a reason. So let's go through and calculate these. All right. First thing to do, XL and XC. Let's write this kind of in the middle over here. X sub L equals, well, XL is just given by definition. It's the angular frequency omega times the inductance. So what is the angular frequency in this case? I didn't write it down. It's 10,000. Be really careful about this number. It's going to be really common in problems. They might give you frequency f, which you're going to have to multiply by 2 pi. But they gave us omega in this case. It specifically says omega equals 10,000, and then it's written in radians per second. If they don't give you this number in radians per second, if it just says revolutions per second or cycle per second or something like that, or it says hertz, it's definitely frequency and not angular frequency. Just keep that in mind. When you see radians per second, though, you're pretty safe. So XL, omega L, so we basically just take 10,000. We multiply by the inductance L, which is 0.06 henries. And that's going to give us an answer of
600.
Is it 600? Is that what it is?
Mm-hmm.
Okay, thank you. And the units ohms, in case you don't remember, one henry is equal to an ohm second. And 1 farad is equal to, I think it's 1 over ohm seconds or something like that. Seconds per ohm, or... What is the equation? The equation is, we'll write it down right here. XL was equal to omega L. XC, which is the second thing we want to calculate, is 1 over omega C. And this gives you resistance. So if we write this one out, this one's going to be 1 divided by omega, which is 10,000. And C is 0.5 microfarad. So what does a farad need to be so that we actually get an ohm? I'm pretty sure you're going to get 500 out of this one. Is that right?
You should get
200.
Is it 200? Okay. Oh, it's because we're dividing by 5. 200. So the farad needs to have units of ohms times seconds, right? No.
seconds over farad, so it should be seconds over ohms, right?
Yeah, that sounds right. And we talked about this last time. I'm pretty sure we got the same thing. Yeah, because this will give us an ohm in the numerator, and the second will cancel with that second. Yeah. Okay, so that's XL and XC. Very easy to calculate. Just plug numbers into an equation. We're going to use those later, though, so it's nice that we have them in advance. The next thing is to find the impedance Z. So the impedance Z is equal to the square root of big R squared plus x sub L minus x sub C whole squared. So this is going to be equal to, big R is 300. I'm going to put the units at the end. So it's 300 plus 600 minus 200. And we square root that whole thing, and these are squared. So squared here and squared here. Pretty sure this is going to be 500.
True.
Because it's 300 squared and then 6 is 4, so 300 plus 400. 3, 4, 5 triangle, basically. Okay, so there's our impedance Z. What's next? The current amplitude I. Well, to find current, we have the equation that says that the voltage of our source is equal to the current maximum multiplied by the impedance Z. So if we take Vs and we divide by I, divide by Z, this is going to give us the current. So the voltage in this case was 50 volts, and we're dividing that by Z, which was 500 ohms. So we are going to get a current of 0.1 amps. That's our current I. This is the maximum current, in case there's any confusion about that. Any questions so far? Very simple, right? Just straight up plug in numbers into equations. All right. It's a nice preview for your engineering courses that are to come. It's a lot of what you're going to be doing in engineering courses. It's just you're going to have equations, you're going to plug numbers into them. All right. The voltage amplitude across. Oh, we missed one. The phase angle phi. Okay. So phi we said was equal to. There's two different ways to do it. We'll just do this method: XL minus XC divided by Z. No, divided by R. Sorry. So this is 600 minus 200 divided by 300, which is going to be 4/3. I think the angle is going to be something like, oh, tangent of phi equals this. I'm so sorry. Make some space here. So this means the tan inverse of this is equal to phi. Sorry about that. So I think we're going to get phi is equal to 53.
Yeah, it's 53.
And then when we convert that to radians, it's going to be like 0.95 something or something. What do you get if you convert to radians?
.93.
Yeah.
So we always want the phase angle to be in radians because omega is always in radians per second, right?
True.
Okay, so there we go. That took up the whole screen, so we'll probably just, for this next part, we'll just keep moving down. The last piece was to find the voltage amplitude across each circuit element. Okay, so what we're going to do is we're going to use our answers here to solve for this part. Let's use a different color. So the voltage amplitude across each element means to find what is VL, what is VC, and what is VR. Okay. So V sub L, we just say it's equal to I multiplied by XL. You already calculated both of these. The current was 0.1, and X sub L was 600. So this is going to be equal to 60 volts. Notice, this is actually bigger than the voltage of the source, right? Did I do that right? I did, right?
Mm-hmm.
Okay.
Yep.
VC, I times XC, is going to be equal to 0.1 amps times XC. XC was 200. So we get 20 volts. And then for VR, we do I times R, which is 0.1 amps multiplied by R is 300, I think. So that's going to be 30 volts. And then, was that it? Was there another piece? think that was the end of that problem. And then we go into the next one. Yeah, voltage amplitude across each element. Okay, so we're done with those. So there's VL, VC, and VR. Again, notice that one of my original questions was, is this going to be true? Is VL plus VC plus VR going to be equal to VS? And you can see very quickly in this circuit that's not true. Because if I sum these all up, I get, what, 110, which is not right. And if I want to actually get 50 volts, well, what can I do?
Subtract. You can add VL and VC together and subtract VR.
Okay, that would happen to work, but only coincidentally, that 80 minus 30 is 50, actually, right? The only way that you can guarantee that it will always give you the right answer is by doing something like this. The true connection between these all is what we saw up here. Oops, where was it? Right here. Oh, this is the third, is right there. That's how they're related to each other. Right? If I want to get 50 volts out of these numbers, the only way I can do it is to take 30 plus, so 30 squared, plus 60 minus 20 squared, square root. Now, your method happened to work in this problem. I wasn't trying to say that doesn't work. It does. But this will always work, basically, is what I'm trying to say. So, you're right. You can't just directly add them, okay? Now we can look at this question next, because the next part of the problem is, it says, this is part 2 of the same problem. For the LRC series circuit of that example, find expressions for the time dependence of the instantaneous current I, the instantaneous voltage across the resistors VR, VL, and the AC source V. Okay? So we basically want to find how do these vary as a function of time. Now this is extremely easy to do, because this is how we started all of this. So let's start with the current as a function of time. We're free to make this whatever we want it to be. We're free to choose one of them and fix it to a certain value. So what I'm going to do is I'm going to force the current as a function of time to be equal to our maximum current I times the cosine of omega t. This just keeps things a lot simpler. If we start with this, we know how to find the rest of them, because we know that the voltage across the resistor as a function of time is basically just I times R. So in here we're going to put IR cos omega t. Now we actually have values for these, so we might as well plug them in. So I times R was the voltage across the resistor, right? 30 volts. So this would be 30 volts times the cosine of omega, which was 10,000 t, right? The voltage across the inductor is going to be equal to IXL times cosine of omega t. But now I have to include something here, and this is where these two mnemonics or whatever help a lot. So if you don't remember what it is, you need E to lead I. So this voltage needs to be ahead by exactly pi over 2. Then we can check. VL, was it supposed to be plus pi over 2? It is, right? And we can calculate what this is, because we know IXL was what we calculated right here. 60 volts. And we multiply that by the cosine of 10,000 t. Oh, whoops. Plus pi over 2. And then V sub C will be IXC. Omega t, we're going to do minus pi over 2 because the current needs to be ahead of the voltage, so we have a negative sign here. This is to be equal to VC, which was 20 volts, times cosine of 10,000 t minus pi over 2. And then finally, the voltage across the source, which is going to be equal to Vs, which is also equal to Iz times the cosine of omega t. And now this is going to be plus or minus phi. But to determine if it's plus or minus, all you need to do is to figure out which is bigger, XL or XC, right? XL is greater than XC, so that means it's going to be plus, because L is the one that leads. And we already figured out what it was, right? when you do an arc tangent, there's more than one solution, right? Technically. Can't you do like pi minus this, and it's still going to work, right?
That's true. That is true.
So that's okay though, because that just means that there's multiple options for what the phase angle can be. So we'll just always probably use the simplest one. So in this case, we got 0.93, and it was positive. So we end up getting IZ, which was 50 volts. That was actually given in the problem, and then cosine of 10,000. And then plus 0.93 radians. That's it. We're done. It's kind of one of those... I mean, I call these plug and chug problems. So last homework is kind of full of them. You'll have to do some thinking, but these problems are very, very straightforward. Any questions? It's been about an hour, so we're gonna take a break right now. Any questions?
I wanted to clarify for the phase angle phi.
Yeah.
Since we're thinking positive because x of L is greater than x of C, right?
Yeah,
Okay.
exactly. Okay, so going on break. I'll stop the recording now.